Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to the Voice of the Cape Matric revision segment for today. We are covering mathematics, and that's paper one, sequences and series. A reminder that this is a recorded session, which means that it will remain on our platforms, Facebook and YouTube, so you can always go back and follow the lesson. A reminder also that there is a link in the description with a link to Intune Tutoring's website offering free worksheets which you can go through. Our guest today is Muntasir Kadri, a private tutor at Intune Tutoring, and I now hand over to him.
Okay, shukran. Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. So today we'll be looking at sequences and series, worksheet 3. So this will be a continuation of when we left off from number patterns last week. So today we'll be specifically looking now at some geometric series and some linear patterns, which are also just arithmetic sequences. And let us jump straight into it. So in example 1, we are given the geometric series. I'll just make it bigger, zoom in, there we go. We are given the geometric series x plus 90 plus 81. So the thing with geometric series is that they don't have a difference as you would find in a quadratic sequence or an arithmetic sequence, where in an arithmetic sequence you'd have a first difference. In a quadratic sequence, you'd have a second difference. But in a geometric series, instead of a difference, what we have are ratios. Right? And I'll show you how we go about solving that. So let me just clear this board quickly. Go. Okay. Okay. Now, first of all, if we look at an arithmetic sequence, just to get this into perspective. Oops. Arithmetic. Right? In an arithmetic sequence, we will have one difference. Right? Right? And what I mean by one difference is we'll have a series, a sequence of numbers, and there'll only be one difference available. Right? So we have a term 1, a term 2, a term 3. And to find our difference, we have to say term 2 minus term 1 is equal to our difference. In a geometric in a quadratic sequence, we'll have a second difference, right? And that just means that after we find the first difference, we have to subtract the first differences because we'll find that the value is not constant. And then we'll end up having a second difference. So what I actually should say here is we have a first constant difference. For a quadratic sequence, we'll have a second constant difference. Constant meaning that it's the same value repeated over and over again. And now for a geometric sequence, what we have are ratios, right? And they'll usually indicate that with the letter R. And for differences, it will be the letter D. Right? And a ratio just means that if we have term 1, term 2, term 3, the ratio is term 2 over term 1. And over here, term 3 over term 2. And this ratio is expected to be constant throughout the sequence. And that determines what the next value is going to be. Okay, now, if we look at this problem, given the geometric sequence, x plus 90 plus 81, and carries on infinitesimally through this lacuna over here, and then it shows at 2.1, calculate the value of x. All right, fairly simple enough. We can actually use ratios to solve this. So if we go here, clear this off. Our sequence was x plus 90 plus 81. So we'll go x plus 90 plus 81. So now we need to solve for x. So we say so this is our first term, our second term, our third term. Our R is essentially equal to term 2 over term 1, but that is also supposed to be equal to term 3 over term 2. So our ratios are meant to be constant. So then we just ignore this R and we substitute our terms in. So term 2 is 90, term 1 is x, term 3 is 81, and term 2 is 90. And now we can solve for x. We just do some cross multiplication, right? And then we'll end up with 90 times 90 equals 81x. And then this just means we have x is equal to 90 by 90 over 81. And our answer for our ratio is going to be, let me just get my calculator here, if I can find it. Oh, okay, here we go. 90 times 90 is 8,100 divided by 81 gives us an answer of 100. And this is our ratio. So our x value is going to be 100. Fairly simple to solve, right? Then 2.2, show that the sum of the first n terms is Sn equals 1,000, bracket 1 minus 0,1 n, 0,9 n. Okay? So how do we go about this? Well, what we essentially need to do is we need to find, and this will be on your formula sheet in your exam paper, we need to find the formula for the sum of a geometric sequence. So if we go here, formula for the sum of we'll just get it up quickly so you can see. Okay, and the formula for the sum of a geometric sequence is, I go here, and here is the formula we need to use. Right? This is for the sum of a finite geometric series. So we'll go Sn equals A times Rn minus 1 over R minus 1. That is essentially what we are supposed to do. Right? And we can actually use either one of these formulas. It'll give us the same value. Right? So let's use the one that looks closest to what we have in the sheet over here. So if you look over here, 1 minus. So this is supposed to be our R value of some sort. So we go ahead and we'll take a look and we'll see this is the formula they used. 1 minus Rn. Okay. Now let's go ahead and we solve for this. So x is a ratio, 0,9. That's correct. That's correct. Right. So R is 100. Okay. So as we can see here, they substitute. If you look here at the original question, we have our x value, which is 100, and our R value, which is what we need to work out. So let me just get this formula. Sn equals A1 minus Rn. Okay, we'll just write it in over here so we can do a recalculation. So we have Sn is equal to A and 1 minus Rn. And this is why we have formula sheets. We cannot remember all the equations that are in. Well, some people can, but I'm not one of those people, unfortunately. I wish I had that gift. All right? And I believe that is correct. 1 minus R. There we go. Okay, perfect. Now, first things first, we need to first find the R value. Right? So we discovered that our R value is essentially the third term over the second term or the second term over the first term. So this is 90 over 100. This is basically 90 over x. So we can say that our R value is equal to 90 over 100. And this means that our R is essentially 0,9. So there we go. We have our ratio. We know our first term in the sequence is 100 because we solved for x, right? A equals 100. And we can double check that. If I go here, we'll see that it's x plus 90 plus 81, right? So if we go back here, it's basically 100 plus 90 plus 81. Okay, so there's our first term, 100. So we have our R, and they want us to solve for this problem. If we go back to this question, they want us to get it in terms of n. So we don't have a value for n. Okay, so now we're going to solve for, we're going to find the sum of the geometric sequence for the value of n. And let's go ahead and we try it. Now we'll go back here and we'll substitute all the information in. So we can go Sn is equal to 100 times 1 minus 0.9 to the power of n over 1 minus 0.9. Now we go ahead and solve it. Right? This is 100 minus 0.9 n over, and what's 1 minus 0.9? Well, that is 0.1. 1 divided by 0.1 should give us 1,000. I'll just double check. That is correct. It gives us 1,000. And we end up with 1,000 times 1 minus 0.9 to the power of n. And that is it. That is our answer for Sn. Sn is equal to 1,000, 1 minus 0.9 n. And let us double check. And there we go. Right, perfectly. The next question states, hence or otherwise calculate the sum to infinity. So there are two different sums that we have for a geometric sequence, right? We have the sum for a finite number. That's when we are given an n value, or we're told to use n terms, because n tells us that there's a specific number of terms we are using, so it's finite. But when we are not told how many n terms to use, and we're told that it's infinity, then we have to use a new sum called the sum to infinity. And the equation we need to use for that is the S infinity is equal to a over 1 minus r. So if we go here, open a new page, we just say that S infinity, and this will also be on your formula sheets, equals a over 1 minus r. And you might be asking, but how do I identify between the different sums and the various sequences that we have? Well, this you can actually see this general pattern amongst them, and you can make that connection and correlation, and you'll be able to see which sum to use for which sequence. In the case of a geometric sequence, if you see the value r within the summation formula, then you know that that's for geometric sequence. All right. So now we go ahead and we substitute the values in. This is 100 over 1 minus 0.9. This gives us 100 over 0.1, which gives us an answer of 1,000. And that should be the answer that we get. So let's take a look. And that is exactly it, right? The sum to infinity equals 1,000 for this specific geometric series for the sum to infinity. Okay, now, the next question asks us to consider the linear pattern 579. Now, this is a linear pattern, and another term for linear is basically arithmetic. So what we'll just do here is we'll consider this an arithmetic sequence, right? And we can double check that it is. So let me just copy this, add it to a new page, put it over here, and let us double check that this is an arithmetic sequence. Now, we can see here that we have a first term of 5, we have a second term of 7, we have a third term of 9. The difference here is 2, and the difference here is 2. So do you see we have a constant first difference? That immediately tells us that we definitely have an arithmetic sequence. Now that we know that it's an arithmetic sequence, we just need to use the formula for an arithmetic sequence to determine the 51st term. And the formula for that sequence is Tn is equal to A plus n minus 1 times the difference. So if we are solving for T51, our first term is 5, so that's where we place the value A. We replace it with 5. The nth term is 51, so we put in 51 minus 1 multiplied by the difference, which is 2, and this will give us our value. So that's 5 plus 50 times 2 is equal to 5 plus 100, and our answer should be 105. Now, let's see if this matches for 4.1. Let's take a look. Let me zoom in. There we go. And there we go, 105, exactly as shown. So, the next question calculate the sum of the first 51 terms. So once again, you might be asking yourself, oh, I look at the formula sheet, what equation am I supposed to use? Well, you just look at what's common with the formula prior. So the normal formula for the arithmetic sequence, the general formula for that, you compare it to the summation formula and you'll notice something common. And if you look over here, here is the summation formula, and we'll just grab this and I will add it to the current page. And if we look here and I compare it, and let me just erase this so you can see, and we compare it to our general arithmetic formula. Look at what's common. Look at this n minus 1d, right? The only difference is 2a. But the fact that you can see this, if I highlight it, look at this. If we ignore the 2, look, we can see that this is pretty much common. And that's how you were able to identify which summation formula to use. So this is the summation formula we're going to use to solve for 4.2. So let's see if we can do it. Okay, I'll move this over here. Let me just clear this all off. So I know that the 51st term is 105. I'll just write this here. We might need to use that later or in this problem as well. So let's take a look. So S for the 51st term is equal to 51 divided by 2, where the first term is 5, we times by 5, plus 51 minus 1 times the difference of 2. This is going to give us, well, we'll just leave this as 51 over 2 for now. Okay. This will give us 10. That's 50 times 2 is going to be 100 plus 100. And that's going to equal 51 over 2 times 110. Okay. And then we can just input this information in our calculator. 51 divided by 2 gives us 25.5 times that by 100, and we get an answer of 2,550. And let's see if this matches. Did I do something wrong? 2 times 5 is 10. Oh, looks like I might have made an error. Let me just double check. 2 times 5 is 10, that's right. 51 minus 1 is 50 times 2 is 100. Right, I did that correctly. Oops. Give me a second. Right. Times 2. Oh, no, they didn't cancel the 2. Okay, so it looks to me like they may have forgotten. Interesting. I don't know why the 2 disappeared here and they got 5 plus 105. That's odd. Yeah, it's not a complex calculation, so something's weird here on the memo. 2 times 5 is 10. 10 plus 100 is 110. If I go 110 times 51 divided by 2, oh, I might have made a mistake. Did I say 50 in the term here? I may have, okay, let me just double check. 51 divided by 2 times 110. Oh, sorry, it is 2,805. I made a mistake on the calculation. Right, so all of this is right. I just inputted my final values incorrectly, and that's why I got the answer wrong. So there we go, 2,805. Yeah, so always double check your answers. It's very natural for humans to make mistakes like this. So just double check your answers at the end of the equation to make sure you did everything correctly. Right? Because the last thing you want to do is lose the final mark, and then instead of getting your full 2, you get 1 because you messed up the final answer. Okay, now the next one, 4.3. Write down the expansion of the sum of 2n plus 3, right? So starting at the value of 1, going all the way to 5,000. Show only the first 3 terms and the last term of the expansion. Okay, so this might throw you off when you see things in summation formula, but don't allow that to throw you off. Let us take a look here. So all we do in this instance, right, is this. So here's the summation formula. So what are they telling us in terms of summation? So if I go here, okay, I'll go back here. Okay. And I can remove this. I don't need this anymore. So if we look at 4.3, what this is telling us, so only for the first three terms and the last term of the expansion. So we know that the last term is going to be a value of 5,000 for n. We know that. And the first three terms starting at 1 is going to be 1, 2, and 3. So if we look at this, this is basically going to look something like this. So we can write down the sum of 5,000, n equals 1, bracket 2n plus 3 is equal. And we just state, well, it's going to be 2, well, you don't have to put all it in, but if n is 1, it's going to be 2 times 1 plus 3, which is 5. Because it's summation, you say plus, you're going to add. Now we look at the number 2 that goes in here, because we're going for the first three terms. So the second term is term 2, where n is 2. So we got 4 plus 3 is 7. Then we use 3. 2 times 3 is 6. 6 plus 3 is 9. Cool. So it's matching that linear pattern so far, 5 plus 7 plus 9, which makes sense. And now we just substitute 5,000 in, which is supposed to be 10,000 plus 3, dot, 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 plus 10,003. And that should match the memo. And there we go. Matches the memo. First three terms and the last term. Now, for question 4.4, hence or otherwise, calculate the sum of n equals 1 to 5,000, 2n plus 3, plus the sum of 4,999 from n equals 1 minus 2n minus 1. All working details must be shown. So this is once again finding the sum for this general term over here. Okay. So if we look at what happens here, okay, they do exactly that. So you look here, they go T1 equals a negative 3. Right? That's our term 1. So let's just check where they get these values from. Okay, so of course the term 1 for this is negative 3. So what you need to do is, we already got the pattern for this one. We know it's 5, 7, 9. I mean, we go here. We know it's 5 plus 7 plus 9, dot, 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 plus 10,003. But then we need to find it for this. So obviously the term 1 and term 2 and term 3 are going to be different for this. Because look, the equation inside here is different, right? So if we had to substitute n equals 1 into here, we get minus 2 minus 1, and that gives us a value of negative 3. And that tells us that for this specific sequence, the first term is negative 3. Right? And that's basically how they got that over here. Then they find the sum, then let's find the value of the 4,999th term. And they just substitute it into the exact same equation as this over here, and they get a value of negative 9,999. Then what do we do from there? Well, we then have to add these two together. So we're going to get 5 plus 7 plus 9 plus 9,009. So they're giving the last three terms as well. Plus, and now they look at the second sequence, negative 3, negative 5, negative 7, negative 9, minus 7, all the way to negative 999. So what do they do after that? Well, they just take this second last value over here. They add it, they say 10,001 plus 10,003 minus 3, minus the first term. Okay, after doing both expansions. And then we get an answer of 20,001. But why did they go about this? Why did they say minus 3? Well, let's take a look at the question. Okay. Hence or otherwise calculate this value over here. All working details must be shown. Okay. So what they essentially did here was, like I mentioned, they added the sums up of all the terms, okay, and they got to 10,003 and 10,001. Then they used the second, they used the second last term and the last term of the first sequence, right? And then they got -3 over here, which was from the first term. And this is essentially how you would go about solving that. Okay? Because if you add all of this up, 5 plus 7 plus 9 plus, and you keep on going, right? Eventually you're going to get a huge value. And the same with this difference formula over here, where you get all the negatives, you're going to get some huge value. And at some point, these values are essentially going to start, we're going to start canceling values out if we had to put the sequences next to each other. Okay? Another way of doing it, in fact, I think a better way, instead of using the summation formula in this manner, you can just go straight to this formula over here, where you put these two together, right? So I would actually prefer to use this, because essentially when they're saying the sum of n equals 1 for this form, right, they're basically using, there's two ways to look at summation formula. You can use it like this, or if we go over here to the worksheet, I'll go back here, right? You can even do this, not that formula, not that one. This is a arithmetic sequence. Okay, so the summation formula for an arithmetic sequence, let me just get it again, which is over here. So I'll just use arithmetic sequence, right? This is the formula we're going to use again. So this is the same as using summation form. It literally means the same thing. Right? So if I go here and I do this for this over here, so we can say that the sum of 5,000 n equals 1 to n plus 3 is the same as using, and let me just get this formula up, Sn equals n over 2, right, is the same as saying, let me do this, Sn equals n over 2, 2a plus n minus 1d. This is essentially saying the same thing, right? So we know we can highlight the things we need. We need our n value, we need our a value, and we need our difference. Okay, so what do we do for the first part? Well, let's first find our first term. We substitute 1 into here because n equals 1, and we get an answer of 5. So that's our first term. What's our second term? Well, our second term, so we know term 1 is equal to 5. We know term 2 will then equal, I substitute 2 into here, will equal 7. We can find the difference by subtracting term 2 from term 1. So our difference is 2. So we can put that here. Okay, our difference is 2. The n value they want us to use is 5,000. Let me put that in here. So we go ahead and substitute directly into this formula. And we get 5,000 over 2. 2 times 5 is 10. Plus n minus 1 is going to give me 4,999 times 2. Now we input this on our calculator, and what's our answer? Let's see. 5,000 divided by 2. Oh, let me just do the brackets first. 4,999 times 2 plus 10 is equal to 10,008. We times that by 2,500. And that's not correct. That's a massive value. Let's just double check the memo. Oh no, it is correct. We do get a massive value. So we get a value of 200 and well, what is this? 25 million 20,000. Is that correct? No. Let me just see it. Yeah, 25 million 20,000. There we go. Is it? 1, 2, 3, 4, 5, 6, 7, 8. That is 1, 2, 3, 4, 5, 6. That's 20,000. That's 5 million 20. Yeah, 25 million 20,000. So we are correct. Okay. So we get this massive number over here. Now we need to do the same thing for this over here. So I'll just pull this over onto a new page. Let me just cut this. Go, add it to a new page, and now we'll try it for the second one. Okay, so all we do is we do the exact same thing. So we have to say, well, we can say Sn is equal to n over 2, right? Just double check, n over 2, bracket 2a plus n minus 1d, close the brackets. Okay, so let's find the first term in the sequence. Substitute 1 into here. -2, -1, so we get -3. So our first term is -3. What's our second term? -2, 2 times -2 is -4, so -5. So what's the difference? It's going to be -5 minus -3, which is going to be -5 plus 3, and our difference is -2. So now we have the a value, which is -3, and we have the difference, which equals -2. Right? So we go ahead and we substitute for 4,999. So we can say S4,999 is equal to 4,999 over 2. 2 times a is just going to be -6, plus our nth term, which is 4,999, so that's going to give us 4,998 instead, times the difference, -2, close the brackets. And this is going to give us 4,999 over 2 times by, let's just see, 4,998 times -2 minus 6 gives me -9,997, which equals this times 4,999 divided by 2. And that gives me a 0.5 value. Let me just see if it's correct. And so what they just did was they just rounded it up. It seems. Let me just double check my calculations are right. Let's do this again. It is 4, okay, and that is -6. That's right. Yes, that is correct. 4,998 times -2 is that, plus -6. Oh, sorry, it's 10,002. That's where my error is. Always double check. Here we go. Especially when you have so much to calculate. I know it's easy to just input everything into the calculator, and then there we go. But sometimes it doesn't always work out. 9,999. So the question asks us to add these two things together. So let's get this value, 25,020,000. So we go here. We write this in. So it's going to be 20,000 subtracted from, but we're adding it together. But of course, I'll show it first like this. That means we're going to end up subtracting because it's a negative value. And our answer is going to be 25,020,123 minus 24,999,999. And that gives us an answer of 20,001. And there we go. That is how you solve that problem. So takes a little bit of doing, but just remember, you can alternate. You can say that your summation formula is the same as this, which it is, right? So don't be afraid when you see this. If this messes with your mind too much, just know that this is the same as this, right? That's a little trick for you out there. Okay, so that brings us to the end of our lesson. I hope that was helpful with regards to sequences and series, with geometric sequences and arithmetic sequences. Luckily, you do get the formulas in your formula sheets for exam papers. So just refer to those and see if you can notice the commonalities between your general formula and the summation formulas. Okay, the worksheet will be available on the Intune website for you to use. You can access it there, download it, practice it yourself, and good luck with the studies and enjoy the rest of your day. Assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum salam wa rahmatullahi wa barakatuh. That concludes our session for today. From myself and my guests, we bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.